afternoon. So I will chair Tezira's presentation. Tezira, I assume it will be you doing this presentation. Tezira will be talking on an ontology for supporting knowledge, discovery, and evolution. Please go ahead.
Thank you so much for the introduction. I'm Tezira, and this talk is around the application of some of the different techniques that we've been looking at this week. It is entitled An Ontology for Supporting Knowledge Discovery and Evolution. I acknowledge the contribution of my co-authors, Deshendran and Tommy. This will be the flow of the presentation. The scientific method aims to bring order to the process of scientific discovery. In philosophy of science, two prominent methods of scientific discovery have been presented. One of them is the inductive theory, in which empirical generalizations are discovered from data. The other is the hypothetical deductive theory of method, in which scientists acquire a hypothesis and test it by checking its predictive success. Recently, Haig introduced ATOM, the abductive theory of method. ATOM consists of two overarching processes, which are phenomenon detection and theory construction. The phenomenon detection process yields phenomena which are unexplainable, relatively stable, recurrent general features that researchers aim to explain. On the other hand, theory construction provides explanations for the observed phenomena. Crossing over to the computing perspective, let me explain three of the systems that attempt to automate the discovery process. The robot scientist by King and his colleagues attempts to hypothetical deductively implement automated systems that execute cycles of laboratory experiments to test and predict the success of hypotheses generated from background knowledge. The disk system focuses on hypothesizing, testing, and evaluating hypotheses originally supplied by the human scientists in order to output a refined hypothesis. The error system uses ontologies to represent clinical domain knowledge and also to construct theories. At this point, I would like to define what an ontology is, because this is in error and because we're going to use it. An ontology specifies the conceptual structure of a given domain in terms of classes or class hierarchies, instances, properties, functions, and even more. Ontologies can be applied in information exchange across autonomous agents or autonomous entities, interoperability, disambiguation, and of course, automated reasoning. Some ontologies have been developed for KDE. KDE is knowledge discovery and evolution. Some ontologies have been developed for this purpose. For example, labels, which was developed for the robot scientists that I've discussed or described, and the disk ontology, which was developed for the disk system. These ontologies follow the hypothetical deductive method, except for HELO, in which the method applied is not exactly explicitly stated. The disk ontology captures the results of executing workflows during the hypothesize, test, and evaluation cycle. We could say that HELO offers some support for scientific laws and hypotheses as statements about phenomena and theories, respectively, though this is not explicit. These ontologies offer really minimal support as shown in this table. For the features that we seek support for, features of agent-based KDE. So what's about agent-based KDE? An agent takes in percepts from the environment, performs some deliberation, and returns an appropriate response or action to the environment. An autonomous agent that performs KDE tasks should be capable of maintaining knowledge about its domain using KR tools and techniques. It should be able to analyze observations, to detect new phenomena using bottom-up techniques. It should also be able to deliberate, to generate explanatory theories for the encountered phenomena and share KDE information, again, by applying KR techniques like Bayesian networks and ontologies, respectively. However, all these communities that I've talked about so far, the philosophy of science community, the machine learning, data mining, knowledge representation and reasoning, and agent-based systems have different perspectives for acquiring information, representing knowledge, and synthesizing or combining information. They have different cultures and they use terminologies in different ways, of course, making interaction difficult. So to solve this problem, we designed a KDE ontology. Its aim is to formalize the KDE process from a top-down, bottom-up philosophy of science and agent-based perspective in order to support an agent-based system for KDE. The ontology aims to provide a shared vocabulary, and it captures information in a systematic way, which aligns with the KDE process that starts with data observations, allows deliberation to construct theories, and also share KDE information. The concepts of the ontology are drawn from Atom because Atom, unlike other methods discussed before, provides a concrete approach for formulating and generating theories. Atom is a unified approach that aligns well with the different AI techniques that are applicable in agent-based KDE. Also, Kuhn suggests that the discovery process starts with the awareness of an anomaly, and anomalies can be detected, and then patterns or novel patterns detected from those anomalies, and these can translate to phenomena, and definitely Atom aligns with this form of discovery. Also, although it has its roots in behavioral sciences, it can be applied in other systems too. In this illustration, we show how Atom aligns with aspects of agent-based KDE from both top-down and bottom-up techniques. So here, we show a KDE algorithm that's based on Atom. In phenomenon detection, when the data quality is assessed, candidate patterns are generated, they're confirmed, and if they're found stable, they're captured as phenomena. When you go down to theory construction, plausible theories are generated, developed, and assessed for their explanatory strength. And at each stage of the process, the patterns and theories are captured along with their provenance information. The ontology uses the Provo Standard. It's designed using UPON and, of course, formalized in OL and Protégé. So these are the concepts of the ontology, or the concepts that the ontology supports. There are two major activities: phenomenon detection and theory construction, and the rest of the activities are actually part of these two. They're not exactly activities, they're just sequences. That's why you see they're actually at the same level. The three main classes are activity, agent, and entity, which are Prof all concepts. And then the three main entities that we work with in the process, as provided or extracted from Atom, would be data, pattern, and theory. And these form the agent-based KDE process. So in this slide, we show the object properties. The entities are the oval shapes and the rectangles represent the activities. This illustration shows how the entities relate and what activities lead to specific entities. So what activity would lead to a plausible theory, or what activity would lead to a candidate pattern, and so on and so forth. The object properties that are prefixed with prof are actually ones that we obtain from the prof or ontology. So if you look maybe as an example, a theory is influenced by a phenomenon, not a pattern. So a phenomenon has to actually be revised until it is, a pattern has to be revised until it's stable, and then it can be, a theory can be generated for it. So theories can be weak theories, strong theories, or plausible theories, depending on the stage of theory construction that they are at. Let me explain with an example. Let us look at the domestic electricity consumption domain. Let's consider these as part of the domain knowledge of the agent deployed to monitor consumption of a household edge. So in this case, households with similar load consumptions are clustered together. Households that belong to the same cluster have similar demographic features. So the agent knows that cluster 1 households probably do not have, okay, well, not probably, but it knows that households in cluster 1 do not have complementary infrastructure like piped water and geysers, and cluster 1 households also do not have appliances, and then maybe like stoves. And then it knows that cluster 2 households own appliances, but they also do not have complementary infrastructure. It also knows that the household that it's monitoring belongs to a certain cluster, cluster 1, and its expected consumption should match the households in cluster 1. This is a reduced example that we draw from work that was done by Webka and from a paper that was published recently by Webka and Moodley. Now, the agent notices an increase in its electricity consumption on summer weekdays. And of course, it notices that the observation or the consumption load actually aligns more with the households that belong to cluster 2 than those that belong to cluster 1. It notices that this is a persistent phenomenon that is stable, maybe that is observed over even the following summer, and it notifies or captures that as a phenomenon in the ontology. So from the agent's beliefs, all plausible theories are extracted. From what the agent knows, new appliance ownership and complementary infrastructure could potentially explain the new phenomenon. Now, to develop these theories further, the agent has to find analogical situations where the theories in question actually explain the observed phenomenon. So in this example, it's done through comparing the demographic characteristics of the original cluster the household belongs to, and then the cluster to which the household could potentially belong. From the data that was curated by Webka, they also collect the demographic characteristics. So that's where we draw this from. The theory, complementary infrastructure, at this point is dropped because, like I explained earlier, the agent sees that it cannot find an analogical situation in this case where this could explain the kind of consumption that we're seeing because it aligns with cluster 2 households which do not have this as a characteristic. All aspects of the theory construction and phenomena that these theories explained are actually captured as part of the ontology, and all these details can be queried. So in this slide, we show 2 example competency questions that are answered basing on the use case using SPARQL queries. For example, in the first query, we want to know what theories explain a given phenomenon, and in the second, how we arrived at a given phenomenon, as in what part of data was used to derive the given phenomenon. In conclusion, we have presented preliminary ontology. The final evaluation of this ontology will be when it is applied to a KDE agent whose architecture is actually still a work in progress. The ontology can be extended to capture features of other scientific methods and actively perform the discovery process instead of merely capturing and querying the discovery task features. That will be it. I want to acknowledge the support of CARE, of HPI, and the Department of CS at UCT. Thank you.
Thank you.